National Electrical Code Section 310.10 addresses ambient temperature considerations for conductors. The code states that conductors and cables rated for operation at over 2000 volts shall not operate at a temperature in excess of 90 degrees Celsius or 194 degrees Fahrenheit. However, there is an exception. If the terminal connections are rated for operation at a higher temperature, the allowable conductor temperature shall not exceed the terminal temperature rating. Therefore, based on this provision, you can indeed utilize the 90-degree column to determine the conductor ampacity for an underground installation, provided that you are using 90-degree rated terminations and equipment. This means ensuring that both the terminations, which are the points where the conductor connects to equipment, and the equipment itself, are designed and rated to handle the higher temperature associated with 90 degrees Celsius operation. When selecting conductors and terminations, it is crucial to refer to the manufacturer's specifications and documentation to verify the temperature ratings. Furthermore, it is essential to adhere to all applicable codes and standards to ensure a safe and compliant electrical installation. The selection of conductor ampacity is directly related to its ability to dissipate heat. Underground installations present a unique thermal environment compared to installations in free air. The surrounding soil acts as a heat sink, influencing the conductor's operating temperature. The 90 degrees Celsius rating refers to the maximum allowable temperature the conductor insulation can withstand without degradation. Exceeding this temperature can lead to premature aging, insulation breakdown, and potentially hazardous conditions. Using 90 degrees Celsius rated conductors in underground applications allows for a higher ampacity for a given conductor size, potentially reducing material costs and installation complexity. However, it's crucial to ensure that all components in the circuit, including terminations, connectors, and equipment, are also rated for 90 degrees Celsius operation. The National Electrical Code provides tables and guidelines for determining conductor ampacity based on various factors, including conductor size, insulation type, ambient temperature, and number of conductors in a raceway or cable. These tables are essential tools for electrical engineers and contractors to ensure that conductors are properly sized to carry the intended load without exceeding their temperature ratings. When working with underground installations, it's important to consider the thermal resistivity of the soil. Soil resistivity is a measure of its ability to resist the flow of heat. Higher soil resistivity means that the soil is less effective at dissipating heat, which can increase the conductor's operating temperature. The NEC provides guidance on adjusting conductor ampacity based on soil resistivity. This adjustment ensures that the conductor's temperature remains within acceptable limits. In addition to soil resistivity, the depth of burial also affects the conductor's operating temperature. Shallow burial depths generally result in higher temperatures due to the proximity to the surface and exposure to sunlight. The NEC may require adjustments to conductor ampacity based on burial depth. Proper installation techniques are also crucial for ensuring the safe and reliable operation of underground electrical systems. This includes proper compaction of the soil around the conductors, avoiding sharp bends or kinks in the conductors, and using appropriate connectors and terminations. Regular inspection and maintenance of underground electrical systems are also essential for identifying and addressing potential problems before they lead to failures. This includes checking for signs of corrosion, damage to the insulation, and loose connections. It's also important to keep accurate records of the installation, including conductor sizes, types, and ampacities, as well as the location of underground cables and equipment. This information can be invaluable for future maintenance and repairs. When selecting conductors for underground installations, consider the environmental conditions to which they will be exposed. This includes the presence of moisture, chemicals, and other corrosive substances. Choose conductors with insulation materials that are resistant to these conditions. For example, conductors with cross-linked polyethylene XLPE insulation are commonly used in underground applications due to their excellent resistance to moisture and chemicals. It is important to understand the different types of conductor insulation and their properties. Some common insulation materials include thermoplastic high-heat nylon, THHN, thermoplastic wiring, TW, and rubber. Each type of insulation has its own advantages and disadvantages in terms of temperature rating, moisture resistance, and cost. Always consult the NEC and manufacturer's specifications to ensure that the selected insulation is appropriate for the intended application. The use of 90°C rated conductors can be particularly advantageous in applications where space is limited. By allowing for a higher ampacity for a given conductor size, it may be possible to reduce the overall size of the electrical system, which can be important in crowded underground vaults or other confined spaces. However, it's essential to ensure that the equipment and terminations are also rated for 90°C operation to avoid overheating and potential failures. The selection of appropriate overcurrent protection devices, such as circuit breakers and fuses, is also critical for protecting conductors from overload and short-circuit conditions. The overcurrent protection device should be sized to protect the conductor at its rated ampacity. It's important to coordinate the overcurrent protection with the conductor ampacity and the equipment load to ensure that the system operates safely and reliably. The NEC provides detailed guidance on overcurrent protection requirements. When working with electrical systems, always follow safe work practices and use appropriate personal protective equipment (PPE), such as gloves, safety glasses, and insulated tools. To energize the circuit before working on it whenever possible. If it's not possible to de-energize the circuit, use extreme caution and follow established lockout/tagout procedures. Electrical work can be dangerous, and it's essential to be properly trained and qualified before attempting to perform any electrical tasks. Consider the long-term implications of your design choices. Selecting high-quality conductors and equipment can reduce the likelihood of failures and extend the lifespan of the electrical system. While it may be tempting to save money by using low-cost components, this can often lead to higher maintenance costs and potential safety hazards in the long run. Investing in quality materials and workmanship is essential for ensuring the reliability and safety of underground electrical installations. Always verify the latest edition of the National Electrical Code for the most up-to-date requirements and regulations. The NEC is revised every 3 years, and it's important to stay current with the latest changes. Many local jurisdictions also have their own electrical codes, which may be more stringent than the NEC. Be sure to comply with all applicable codes and regulations. The NEC is not a substitute for professional engineering judgment. Electrical engineers are trained to analyze complex electrical systems and make informed decisions based on sound engineering principles. If you are unsure about any aspect of an electrical installation, consult with a qualified electrical engineer. When planning an underground electrical installation, consider the future needs of the facility. It may be prudent to install larger conductors or raceways than are currently required to accommodate future load growth. This can save time and money in the long run by avoiding the need to upgrade the system later. Proper grounding is essential for the safety of electrical systems. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protection device and prevent electrical shock. The NEC provides detailed requirements for grounding electrical systems. When working with underground electrical systems, be aware of the potential for stray currents. Stray currents are unwanted electrical currents that flow through the earth. These currents can cause corrosion of underground metal structures, such as pipes and cables. There are several methods for mitigating stray currents, including the use of grounding electrodes and cathodic protection systems. Consider the aesthetics of the installation. While functionality and safety are paramount, it's also important to consider the visual impact of the electrical system. Choose materials and equipment that blend in with the surrounding environment. For example, underground transformers can be used to eliminate the need for unsightly overhead transformers. Document everything thoroughly. Keep detailed records of the installation, including conductor sizes, types, ampacities, grounding information, and overcurrent protection settings. This information will be invaluable for future maintenance and troubleshooting. Before backfilling an underground trench, be sure to inspect the installation carefully to ensure that all conductors and equipment are properly installed and protected. Use appropriate backfill materials that will not damage the conductors or equipment. Compact the backfill thoroughly to provide support for the conductors and prevent settling. Consider the potential for future excavation in the area. Mark the location of underground cables and equipment clearly to prevent accidental damage during future digging. One-call systems, such as 811 in the United States, can be used to locate underground utilities before digging. Always call before you dig to avoid damaging underground utilities. Underground electrical systems are subject to a variety of environmental factors, including temperature variations, moisture, and chemical exposure. These factors can degrade the insulation and other components of the system over time. Regular inspection and maintenance are essential for identifying and addressing potential problems before they lead to failures. When performing maintenance on underground electrical systems, be sure to follow safe work practices and use appropriate personal protective equipment. To energize the circuit before working on it whenever possible. If it's not possible to energize the circuit, use extreme caution and follow established lockout/tagout procedures. Electrical work can be dangerous, and it's essential to be properly trained and qualified before attempting to perform any electrical tasks. The exception in NEC 310.10 allows for the use of the 90°C ampacity ratings if and only if the terminations are also rated for 90°C. This is a critical point, as using terminations rated for a lower temperature would negate the benefit of the 90°C conductor and could lead to overheating and failure at the termination point. Manufacturers typically mark the temperature rating of terminations clearly on the device. This rating should be verified before installation to ensure compliance with the code. The 90°C rating is not a blanket approval for all underground installations. The specific conditions of the installation, such as soil resistivity, burial depth, and ambient temperature, must be considered when determining the appropriate conductor ampacity. Adjustments to the ampacity may be required based on these factors.